So we were looking at the pyrimidine analogs, and when we looked at most, and I asked you to also look at them, when you look at the structures of the pyrimidine analogs, either there's a change on the sugar moiety, so you can have the drug as a nucleoside, as I said last time, or you can have structural modification on the sugar or structural modification on the base itself. And once you have that structural modification, it does not allow for the continuous synthesis of the DNA, and therefore that process will be blocked. The other second, so that was the first type where we have the pyrimidine analogs. You can also have the purine analogs, and I think we mentioned a few of them. You can see that is 6-mercaptopurine. The normal one, of course, does not have a sulfur. Usually it has an oxygen at that position. You can also have, so the only difference between this and this is the structure. Just a structure that in this position, we have an amino group. That one, this is just a basic purine. This is now a specific purine, which is guanine. But now it becomes a guanine because of that SH. So if you go through these structures, you can see the differences. You'll be able to note that the structures are a bit different. You can see there is a chloro group there. That makes a difference. And once you make that difference, then definitely. If you see this one again here, and see this, that's amino group CH2OH. I believe it's this hydroxy group, which is different, having a different orientation than the ones which is usually vertical for the ribose. So this is carrying a horizontal orientation, making it very different. And then this one, you can see the fluorine. So if you look at all these structures, you will see there's a lot of structural difference. There is a lot of structural similarity, a small structural difference that brings in the change over. The pentostatin, that's a 7-membered ring rather than the kawaida 6-membered ring, and that for sure brings about a difference in activity. So that is the second one, where we have also the purine analogs. You can also have folic acid analogs. And at times the folic acid analogs, because the folic acid derivatives, the folic acid derivatives are usually affect the folic acid. Sorry, folic acid is used. Derivatives are used as cofactors, and cofactors, remember, can be used in both purine and pyrimidine synthesis. So the folic acid and analogs ultimately will have an influence on purine synthesis and pyrimidine synthesis, and its metabolites, especially tetrahydrofolate, is a cofactor. Remember, cofactors are used in metabolic processes. Like the cofactors are used in purine synthesis, they are used in pyrimidine synthesis. So if you do not have the cofactor that you require, ultimately you will have an influence on the purine synthesis or on the pyrimidine synthesis. So when you look at the folic acid analogs, they will have an effect on both purine and pyrimidine synthesis. So you're looking at examples of the folic acid analogs are methotrexate and pemetrexate. Again, folic acid analogs are not very new to us, because when we discussed the sulfonamides. Sulfonamides and the sulfones. Sulfonamide, we said, they block operation of para-aminobenzoic acid. They block the dihydrofolate. They block the dihydrofolate synthesis enzyme, and are actually also, we consider them to be antimetabolites. So this is not the first time we are encountering the folic acid analogs. So when you look at this, is a folic acid. So this is the structure of the folic acid. This portion here is usually the pteridine. This portion up to here, there, going this way, that way, all that coming up to this methyl group there. That is the pteridine. If you look, I think the other one last time was quite good. If you look now from here, from this amino group, where I'm pushing the cursor, from that amino group coming all this way up to there, that is our para-amino benzoic acid in here. After I think I like here, I don't know how we had done the other one. Like the other one I could point very easily. Yeah. So all I'm saying is that when you look, so from here, and we had done para-amino, from there, this is where we start our para-amino benzoic acid, come this way to there. Para-amino benzoic acid, that's a PABA. That's how we are able to use the sulfonamides. Then, of course, from there going this way is a glutamic acid. So you find that when we look at now the antimetabolites, the folic antimetabolites, they must have a structural similarity with folic acid, but also a difference. So if you look at the first one, we have methotrexate, and you can see the pteridine area, because I've said this is the pteridine area. You can see the pteridine area, because you can see at this position here, you have an amino group, but in folic acid, you have a hydroxyl group. Of course, in introduction of an amino group, we make the molecule basic. So that could have an effect on the activity of binding of methotrexate compared to folic acid. So that's one difference. When you come at the joining group here, this is an amino methyl group. If you look at this, the amino group, the nitrogen is replaced with a methyl group to give us almost what we can say almost a dimethyl amino. So that again, one, introduces steric hydrons. Two, amino groups, this methyl group is an electron pusher, so again increases the basicity of that nitrogen. So again there, we do have a structural difference. So a structural difference there, a structural difference there. If now you look at the other structure, it is the same. We are retaining this structure to be the same. The enzyme is confused. So I mean, if we put it in that manner, so that now the enzyme does not differentiate. The structures are so similar that the enzyme is not able to differentiate between folic acid and methotrexate, and therefore, once it takes the wrong substrate, like of course, you remember folic acid has to undergo reduction to dihydrofolate, using dihydrofolate reductase to tetrahydrofolic acid. So enzyme dihydrofolate reductase will not be able to differentiate between folic acid and methotrexate. If it takes methotrexate, that's the end of the story. The process will not continue. So please note that minimal structural difference. Then you have the pemetrexate. If you look at pemetrexate, yeah, that is a ketone, that is a hydroxyl group. And then look at this position. We have the pyro group there. That's our pyro group. And like here, we have our pyrazine group. So again, that structural difference between that ring and that ring, that again gives us a lot of, gives similarity, there's structural similarity, but there's also structural difference, so that this molecule will bind differently to the enzyme and therefore bring us stop. There is no continuity. That is an amino methyl group, as we had said. Now, again, if you look at this as a portion, the same. So please let us understand that we are changing the molecule, but making sure that it binds, it is recognized by the enzyme, but when it binds, there is termination of the process. Now, if you look at trimetrexate, look at trimetrexate again, that's an amino group making the molecule more basic. That portion there is the same. But look at this group here. Now we if you start putting 1, 2, oxybenzene. 1, 2, 3, trimethoxybenzene in place of our para-amino glutamic moiety. So in place of the para-amino benzoic acid glutamic moiety, we have put a new molecule, and therefore again not allowing for the continuity of that process. And once that happens, of course, that compound will act as an anti-metabolite. So those are the 3 classes that we concentrate on. We are going to look at them later. We are going to concentrate on the purine analogs. We're going to concentrate on the pyrimidine analogs. Of course, the folic acid analogs, which I've said, they do have a connection to both the pyrimidine analogs because they are indeed cofactors. Then we have the anti-cancer antibiotics. Can you remind me what is an antibiotic? What is an antibiotic? What is an antibiotic? I have to keep giving myself a small break because my chest. In colleges, you find 2 lectures for per unit. So you can allow for each other to teach you in case someone is unwell. But since as we teach 1 unit at 1 lecturer, you have to do the best you can. So can you remind me what is an antibiotic? Can you remind me quickly? Let's move very quickly. What is an antibiotic? So an antibiotic, you have remembered, we had looked at that. So we are saying medicines that you need microorganisms such as bacteria, drugs that slow down the growth of bacteria or kill bacteria. But we had said a little bit more details. What had we said is the difference between an antibiotic and an antibacterial agent? We had said a little bit more than just that these are substances that kill bacteria. You can always refer, but I know we had said a little bit more in terms of their source. Look at that, but thank you for those who have tried. It was still a good attempt. So, so we are looking at the anti-cancer antibiotics, and we have quite a number of them. Some of them structurally related, others not structurally related. So we have one of the first ones was actinomycin D. Actinomycin D, also so that was the first one. Then you have bleomycin, you have mitomycin C, the anthracyclines. So here we have something similar to the tetracyclines. These are the anthracyclines, similar to the tetracyclines. And under the anthracyclines, you have doxorubicin, daunorubicin, idarubicin, epirubicin, and vaorubicin. And then we have also streptozotocin. Remember we had mentioned streptozotocin as a nitrosourea. But that does not stop it from being its actual mode of action. Its source. The source is the one it is putting it under the antibiotics. So if you look at the dactynomycin, we are going to look at it, but if you look at this structure, you can see some very significant features. You can see these are amino acids. You have a pentapeptide here. 1, 2, 3, 4, 5. Pentapeptide here, both on that side and on that side. You have 3 rings here. You can say this, of course, is a peptide, and this is a penoxazine ring. This is a penoxazine ring. Anti-cancer, the proica agents, the anthroproic agents, we did come across such a ring. So it has very unique features. It is an antibiotic, and we will see how its mode of action as we move on. Then we have the anthracyclines, and you can see they have 1, 2, 3, 4, very, very similar to the tetracyclines. Even the numbering, you can see, very similar, even just like the tetracyclines, where A is an aromatic ring. You can see the same is maintained for these drugs. But of course, they have differences in their substituents. They have differences in their substituents. They have also differences in the way the ring is numbered. Remember, for tetracyclines, we start here. For these ones, we are starting the numbering from that. Ring D carries position 2. Then we have 5. So again, you can see we are living, just like in the tetracyclines, we are leaving the intersection 4, 5, 6, 7, 8, 9. So we just go around 9, then 10, 11, 12. So the numbering a little bit different, but you can see just like the tetracyclines, they have 4 annulated rings, and indeed the numbers are up to 12. The carbon numbers are still up to 12. All the rings are carbocyclic. a structure like anthracene ring, just like the tetracyclines and that. So in that way, they belong to the same class in terms of the basic structure. But now when it comes to substitution, the substitutions are different. You can't see this this has a sugar, so you can see these strands, all of them a glycosidic linkage. Sugars, unlike what we looked at when we were looking at the tetracyclines. So that is a numbering. At position 7 of all of them, they have a sugar moiety. They have that sugar moiety. Again, we look at the details of that. The only thing we need to establish right away, if you look at doxorubicin, you can see it has at position number 4. If you look at also the ulorubicin, it has a methoxy group at position number 4. But if you look at the position number 9, look at the position number 9, then the position number 9 is different. This has hydroxymethyl ketone. So you can see this has an alcohol, it has a ketone and an alcohol, and that position, you can see this one has an acetyl group. So this, on the side chain, it has still oxo group, whereas this one is an acetyl. So that's the main difference between the doxorubicin and daunorubicin. If you look at idarubicin, you'll see a very major difference that these two have a methoxy group. At that position, idarubicin does not have a methoxy group. And idarubicin is more structurally similar to daunorubicin because of the acid, but it does not have a methoxy group at position number 4 of the structure. So it does not have a methoxy group at position 4 of the structure like these other ones. Now, if you look at epirubicin, you can see this epirubicin and epirubicin and doxorubicin. Yes, I think this is doxorubicin. Yeah, and doxorubicin, you find this is the epimer. Epirubicin is the epimer of doxorubicin. If you look at the hydroxyl group, this hydroxyl group here, you can say this is, we consider that this is position 1, position 2, position 3, position 4. Now position 4 prime. It's position 4 prime of the sugar. I've just counted. You can count it. I've just counted from the oxygen. In fact, we should count this way because of the subsequence. So we can say position 1, position 2, position 3, because if we count that way, the substituents will have the lowest number possible, and that is the UPAC system. So that is position 1, position 2, but of course these are the primes. So if you look at the position 2 prime, you can see the sugar. This is epirubicin. I have to be here. Sugar. Epirubicin, yes. This one here. So if you look at position 4, this sugar, the one that is epimerized. And because of the epimerization of that sugar, this sugar at this position, this sugar here at this position, is the one which is epimerized. And because of that epimerization, that sugar and this sugar do not, so not sugar, sorry, the hydroxyl group, sorry. This hydroxyl group at position 2 prime and that hydroxyl group at position 2 prime have a difference in the orientation, and that therefore one is an epimer of the other one. Remember we said an epimer take different orientations, and one therefore if one was having an alpha, the other one takes a beta, and therefore they are epimers, but the structure is the same. So again, we will come back there and we will be able to look at those drugs, and then of course we also have mitomycin also as an antibiotic. And the plant products, because we do have plant products that are used also as anti-cancer agents, and the plant products are further classified into different according to their mode of actions. So we have, it is a plant product originating from the plant, but the compounds have different modes of actions, and therefore they can be further classified into different modes of action, but in both, all of them are mitosis inhibitors. Remember when we were looking at the cell cycle, we talked about the M phase and phase. And the M phase, we divided into mitosis and the cytokinases, and therefore we are talking about the mitosis, which is very important because the mitosis is where the organelles divide and the cytochrome divides and ready for cytokinases, where the whole cell divides. So if you block mitosis, that means there will be no replication of any of the components within the cell. The DNA will not replicate, the organelles will not replicate, the chromosomes will not replicate the structural protein. So there will be no replication. There will be no cell division. So for sure, the cells, they will stop the growth and development of that particular cell. So must look the which are tubulin inhibitors. You can have those which are tubulin inhibitors, where you have the vinca alkaloids. Then you look at them later, where there is no internet. What has happened? Funny things. So, but now we are looking at taxose derivatives as the plant, and then of course there's still tubulin inhibitors, still mitosis inhibitors, and you have paclitaxel and docetaxel, and then you have also camptothecin derivatives, again where you have camptothecin, irinotecan, and topotecan. So these are these are a particular group of plants, particular group of plants. Hello? And 7,000. Bypass. I'm in class. Nasema niko kwa class. Nimesahau hiyo jina nitakwambia. So then you have the second type of mode of action where they can be topoisomerase poisons. This again, the topoisomerase are enzymes that are required in replication. And the derivative we have there is a pipo-tophyllotoxins, etoposide, and tenol. This would be tenoposide. So we have tenoposide and etoposides, which again are specific in their mode of action. They will inhibit that enzyme and therefore inhibit mitosis. So all those are plant products that have also been found or are used currently as anti-cancer agents. And of course, after that, I've shown the difference. So the plant products, and you have the first one, vincristine and vinblastine. You can see they have quite a complex. They have quite a complex structure. They have quite a complex structure, and they differ at this position here. Vincristine and vinblastine, they differ at that position, where for vincristine, it is an aldehyde, as you can see there. And in vinblastine, it must be a methyl group. So it can either be an aldehyde, and that makes a difference. So of course, those are vinca alkaloids. Then you have the camptothecin derivatives, and we can see you have the camptothecin itself, irinotecan, and topotecan. And again, their basic structure is the same. You can see this quinoline derivatives. That's quinoline derivatives. Their basic structure is the same, but they can differ in the subsequents that are found on the phenyl ring of the quinoline. The quinoline structure. That you can have that is the R and R prime. So that is the area they differ. Otherwise, the rest of the structure. So we can actually draw that and draw a ring like this and call that R. And that R is basically the same. It doesn't change. These camptothecin derivatives. What changes is these two groups. And when you look at the camptothecin itself, we find that this R is a hydrogen and that is a hydrogen. So that's the simplest of the structures. And then when you look at irinotecan, this becomes an ethyl group. That is an ethyl group, and then this comes, and you can say this an acid. C double bond O, an acid derivative of this. This is piperazine, and that is piperadine. So you have the piperadine, piperazine. So in fact, you can even call this an ester. Actually, this is an ester. SCOC double bond. Oh, it's an ester. Yeah, that's an ester derivative. So this is an ester group there, just an ester group there, and then joined to piperazine, piperidine. Piperazine is a piperazine ring, and that's a piperidine ring. So an ester joined to a piperidine ring, and of course that there is an ethyl group. Then you have the topotecan. You can see this is a dimethyl amino methyl group. Dimethyl, this is a dimethyl amino methyl group, and the second group here is hydroxyl group. So what is important for us is that the larger portion of that molecule is the same, and the difference in these different drugs is the substitution on the benzene ring of the quinoline ring, which also, the quinoline ring is also a basic part of the basic structure. So the substitution on the benzene ring is what is changing. So that makes the compounds a bit easy to know, because it's only R and R1 which is changing. Although the structure R and R prime which are changing. And then we have the next, which we had also mentioned, is the phyllotoxins, and under that you have the toposide and the teloposide. And again, if you look at this structure, they are saying the whole of this structure from here, these drugs, all the way here, all this, you can call that an R. All of that, you can call that an R, because that R remains the same in all these drugs. The only area which is changing is this R here. So we can call this, because we already have an R, we can call this or this, let's say R1, to just make the difference. So that is the only area which is changing. It's a very small area. That's the advantage of this compound. It's a very small area which is changing. And of course, that small area changing, it will have an influence on the lipid solubility of this molecule. It will have an influence on its ability to bind. It can have steric hydrons. It can have an influence on the polarity. And those are the things that will influence the binding of that drug. So in a toposide, you find that R is a methyl group. And in teloposide, you find that R is a thiophene. Again, thiophene is not a new molecule. This is a molecule that we just studied when we were looking at the cephalosporins and the penicillin. So here, it can be a thiophene or it can be a methyl group. When it is a thiophene, it's teloposide. When it is a... So those, again, are the slight changes that have been done to give us drugs that have been found to also have anti-cancer activity. Then the next category, remember, we are still on plant products. We're just looking at the various structures. Again, look at the big advantage, a very big structure, very complex structure. But in the derivatives, that structure is remaining the same, and there's a very small R group, which is changing. So you have the cell in the paclitaxel. As you can see, there's also another one somewhere. Sorry about that. Yeah, here it is. So there's that change there and that change here. So for paclitaxel, that R here is another phenyl group like that one, a phenyl group, and R1 is an acetyl group, making this an ester, because you will bring in here CW, you join the R1, you remove it and you join, and the first thing you double bond O and then CH3, and because we have this oxygen, that will be an ester. So in paclitaxel, you have an ester there. You have an ester there, and of course a benzene ring there. In docetaxel, you have an acetyl group, but it's a substituted acetyl group. You can see the normal acetyl group is CH3, C double bond O. So here you have it's an acetyl. It's a type of acetyl group, but in fact, we cannot call it acetyl because it will have one carbon, and these are 3 carbons. That will be 4 carbons. Acetyl should have only 2 carbons. So it will be like it is a derivative of butane. It's a derivative of butane, but it's an acyl group. Acyl groups is where you have C double bond O. You can see this is a tert butyl acyl group. Tert butyl acyl group, because this is CH, it will be in sorry, so it's not an acyl group, it's an ether, sorry about that, it's an ether, because this CH3, this carbon is attached to a CH3, attached to another CH3. I wish I can draw for you. I don't know whether I can. Yeah, it can draw. That's a C, the one we are talking about is the middle one, and then it's attached to there's a carbon, a methyl group, and I never worry that I'm attaching them directly. So what we are saying is this one, remember, this is standing for CH3. Yeah, so all these are the same. So CH3. So all these CH3s are attached to a carbon. So they are attached to this carbon here. So the carbon there. So if they are all attached to that carbon there, what we are getting left is an oxygen. So that resultant group is actually an ether. The docetyle has an ether at that position. That is a tert butyl ether at that position, because we have said this carbon, this CH3 cannot float. So it has an ether at that position, and at this position it has a hydrogen. So that is the main difference between those two. So for this, for paclitaxel, it has a benzene and it has an acetyl. And then you see, like now, this one you can tell it's an acetyl because this group must be satisfied. So this cannot be an ether. So this oxygen must be coming here. That's what I'm saying. It must be coming there. So that, like that. Because the carbon must be satisfied. It must be coming like that. So this carbon is this one, and then this oxygen, double bonded oxygen, and that. And if you look at this carbon now has 1, 2, 3, 4. So we must be able to, when we have the condensed formula, because it's a condensed formula, you must be able to write it out. Must be able to write it out when you're doing the structure. So that means this is an acetyl group, this is an ether, tert butyl ether, as I have explained, and that makes a difference. Of course, this group here, because of the tert butyl here, tert butyl, it is having an increase in lipid solubility, even also as it increases the steric hydra. So those are some of the structural differences that can bring differences in the binding to the receptor, and even in distribution, because we did mention earlier that the level, of course, we have always mentioned that the level of the lipid solubility will have a major influence on the distribution of a certain drug, especially to the BBB. So this one is the same we have looked at. Now here, it's just drawing the structures out. It's just the same structures that we have looked at. I've just drawn them out. So the same thing here, the same structures we have looked at, only drawing them out, nothing new. Then, so that is the plant product, both whereby you have the tubulin inhibitors, the topoisomerase inhibitors, and of course belonging to different products of different plants. Then you have the protein kinase inhibitors. And under the protein kinase inhibitors, you have different compounds. You have the imatinib, you have the dasatinib, you have the gefitinib, and erlotinib. And you can see again whereby we have in pharmacology, we used to teach nomenclature. When we're looking at nomenclature, we look at names of drugs. And if you look at this, you can see they all share the end here. And normally when drugs have some similarity in their naming, it either means they have some structural similarity or they have similar mode of action. There's something they must share. So of course, all this, they of course really have structural similarity. As you can look at them, they have different structures. There could be slight structural similarities. They look very bulky, but what they do share, they share the mode of action. They have a similar mode of action. But even from a glance, you see that they have a lot of nitrogens, but they also have a lot of hydrocarbon sections. So they share a similar mode of action. Imatinib, dasatinib, gefitinib, and erlotinib. And erlotinib, all of them being protein kinases, inhibitors, and as I have said again, you look at them in details in a minute. Then we have the monoclonal antibodies. You have the rituximab, gemtazumab, and ozogamicin. Again, not say much about them because they don't have a lot of structure and so on. So the miscellaneous, as I said last time, there are different ways of classifying these drugs. Whatever I put here as miscellaneous, you might find in another classification, it's put in a certain classification. So it all depends on the criteria the person who was classifying used. So you have the L-asparagines, you have arsenic trioxide, you have hydroxyurea, and tretinoin. I have an example of tretinoin, and you can see the conjugated double bonds there. Then you have the hydroxyurea, just urea and hydroxyl substituent. Then from there, you have another big class, which you call the hormonal drugs. And under the hormonal drugs, we'll have several subclasses. We'll have several subclasses. You have the glucocorticoids. You have the glucocorticoids. And I believe, I don't know whether you have done the steroidal, non-steroidal anti-inflammatories, or not on the steroidal drugs, or you've studied the steroidal drugs anywhere. And if you studied, because what we are doing were the non-steroidal anti-inflammatories, if you study the steroidal drugs, because most of them will cause a hormone, you see that they share the steroidal hormone, they share this complex structure here. The steroidal structure is this one here, like this, coming like that, coming like that. Of course, we remove let's remove the. So let us start here. So we come like that, like this, this. That is a steroidal structure. So whenever you find a drug having those four rings, then you see it has the steroidal structure. So that so we have the glucocorticoids, which are also, they have an influence on the glucose. They have an influence on the glucose, increase levels of the glucose, and therefore they can trigger diabetes. So we have prednisolone, and we can also have prednisone. We find that prednisone and prednisolone differ only in this hydroxyl group in this position, where for prednisolone, this hydroxyl group, for prednisone, this is a ketone. So prednisolone and prednisone, you can have them as hormonal drugs. And one will have a ketone, which is prednisone, and prednisolone will have a hydroxyl group, and prednisone is usually metabolized in the body to prednisolone. Those are the glucocorticoids. We are looking at the hormones that we have been used as drugs. Again, we're going to look at them in details. You have the estrogens also. You have the phosphestrol and ethinyl estradiol. This is the ethinyl estradiol. Of course, the difference between the estrogens and the other hormones is that the estrogens will have an aromatic ring. Their first ring, this ring, will be an aromatic ring, when you look at the other hormones, that ring will usually not be an aromatic ring. It can have unsaturation, as you can see, but to not be an aromatic ring. Once it becomes an aromatic ring, more often than not, the drug will change to an estrogen. Of course, the substitutions may differ, but the major difference is in this ring, where in estrogens, through utilization of the aromatase enzyme, that ring is derivatized into an aromatic ring. So that, of course, this is a synthetic estrogen, and also, of course, ethinyl estradiol, which is a semi-synthetic estrogen. So that's another class. Then the third class under the hormones, you have selective estrogen receptor modulators, where we have tamoxifen. I don't remember the structure of the other one. Oh, I think unfortunately I picked the wrong one. But I'll bring you the structures of both of them. I drawn them, but unfortunately when I was picking the notes, I picked the wrong one. So that is tamoxifen again, which is a selective estrogen receptor modulator. Then we are going to look at them, selective estrogen receptor downregulators, like falfistrat. Again, that's a steroidal derivative. And of course, you can see it's an estrogen. That is an aromatic ring. Then you have aromatase inhibitors. As I have said, there is conversion of the steroidal derivatives converted into specific estrogen derivatives by the aromatase enzyme. The aromatase enzyme is responsible for aromatization of ring A. We also have the antiandrogens, and under the antiandrogens, of course, these are synthetic. You have flutamide and you have bicalutamide. And then you have the progestins, which where you have the hydroxyprogestin. Here the structure. Please correct this structure for hydroxyprogesterone acetate. For this to be acetate, cut this off. It will end here. For it to be an acetate, cut it off here. This will not be there. Because I'm mistaken during that structure. Again, I had corrected it, but when I was transferring, I think I made a mistake. So this will be CH3. So here, at the end here, will be C, double bond, oxygen, CH3. So I'm saying you remove the whole of this section. So this ends here at CH3. It is hydroxyprogesterone, because progesterone does not have this hydroxy group here. If we are talking about progesterone, this group there will be replaced with a hydrogen. Progesterone, that group is a hydrogen, and that's why we are calling it hydroxyprogesterone. And then acetate, hydroxyprogesterone, acetate, because of the fact hydroxyprogesterone acetate, because of the fact that that's a CH3 double bond O, so acetate. And of course, because it's an ester, that's where the acetate is coming in. So this CH3 C double bond O is a unit group which is responsible for the acetate. And of course, we call it an acetate because of the fact that it is an ester. But under normal circumstances, progesterone does not have an oxygen here. So because of the introduction of the oxygen there, and that oxygen is the one which undergoes, which where you have addition of an acetyl group, we call it hydroxyprogesterone. But as I have said, the acetate is now because of the fact that now you have an acetate group at that position. So that is also in a hormonal drug, which is used as an anti-cancer agent. Then you have also 7-alpha reductase inhibitors. Again, you have the finasteride and dutasteride. Again, you can see these, again, are steroidal derivatives. They will have their structural differences. They will have structural differences, so that you see these 5-alpha reductase inhibitors, 5-alpha reductase enzyme, it's part of the body. And therefore, when you get a drug or you get a compound that has structural resemblance with the substrate, that it can be recognized by the enzyme, the reductase enzyme, but it's not exactly the same. When it is taken up, it blocks the enzyme and immediately you stop the process. Then you have the gonadotrophin, release luteinizing hormone analogs, gonadotrophin releasing hormone analogs. Again, we have examples where we have nafarine, leuprorelin, and tryptorelin. Again, these are complex structures. They're not even structures anybody can ask you to do. They're very, very complex. But again, see, they are influencing, they're having an effect on the naturally occurring compounds, on they have structural resemblance with the gonadotrophin releasing hormones, and because of that, again, remember, these processes are blocked. These processes have a negative, are controlled by the negative feedback mechanism. So when you have analogs that have similar activity, like the natural occurring compound, that means they block the synthesis of the natural occurring compound and usually stop that organ from functioning. So you find that you find that the mechanism of action of these different hormones can be the same, but all we are looking at, we are trying to imitate, or we are trying to have structural analogs of what we have in the body. And once you have those analogs, they'll be able to block the natural occurring mechanism. Gonadotrophin also releasing hormone antagonists, those are analogs, these are antagonists. Either of them will work the same. So we have the cetorelix, ganirelix, and ambarelix. Again, sharing very common names because of similar modes of action. Again, you'll be able to look at them. Then you can also have immunotherapy, where you have the interferons. Again, because we will do more about this in pharmacology, I will actually mention it in passing. So those are the various classes of drugs that you'll be able to look at. If there's any I have left out, we will actually add it on just in case. So the first thing I want us first to appreciate, and I believe all of us do understand. I don't know why it has changed again. What I want first to appreciate, and you have done this, is the DNA. And we know when we talk about the DNA, we say the DNA is a double helix. It's a double helix. And the D stands for deoxy. The D stands for deoxy. And when we talk about the deoxy, we are looking at the ribose sugar. And the ribose sugar at position 2' usually has a hydroxyl group. The ribose sugar at position 2' has a hydroxyl group. When we talk about the deoxyribose sugar, then at position 2', the hydroxyl group at position 2' has been replaced by a hydrogen, and therefore deoxy. So that's the first starting point. We have deoxyribose. Deoxyribose means the ribose sugar at position 2', the hydroxyl group, which is usually in the ribose sugar, has been removed and replaced with a hydrogen, and that's what we call the deoxy. You find, of course, the RNA has the ribose sugar, the DNA has the deoxyribose sugar, and no wonder the name. One is a ribose nucleotide, and the other one is deoxyribonucleotide. So that explains, that name is because of this position. So when you look at this position, this is our ribose sugar, position number 1'. Let's call it prime because we have the other structures. 1', 2', 3', 4', 5'. And all we are saying is when you look at the ribose sugar at 2', you have a hydroxyl group. And that is what forms the RNA. When we look at the DNA at position 2', this hydroxyl group is replaced with a second hydrogen. So you can see these are two hydrogens at position 2'. This is a hydrogen and a hydroxyl group at that position. So let's be clear. But remember, sometimes when they draw this arrow, remember line nomenclature puts, when you leave an arrow like this, means it's supposed to be a methyl group. But remember, it is a hydrogen. It is a hydrogen at that point. They're just supposed to draw a short line. Or if they draw it like this, they make sure they put a hydrogen so that you're not confused. But remember, this is not a methyl group, that's a hydrogen. So this is what we find in RNA. This is what we find in DNA. So once you look at the DNA and we say that the DNA is a double helix. So this is one of the helixes. One of the helixes, one of the strands. So each of the strands, you can see it will have a specific base. And of course, the base, the name of the base is dependent on the structure. So if you look at this is adenine. Adenine has only one substitution. It has only the amino group. It does not have a substitution at this position, which is position 1, 2, 3, 4, 5, 6, 7, 8, 9. No, this is the 9. So sorry, we start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, supposed to start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it does not have 1, 2, 3. It does not have any substitution at position 3. So that gives it adenine. Because it is a purine, it is bicyclic. These are details that I hope you know. Then when we come to guanine, now the difference between adenine and guanine are 2. 1, of course, in guanine, it has an oxo in place of the amino group at position number 1. And then at its position number 3, it has an amino group. So it has 2 substituents, and position 1 is an oxo, unlike adenine, where position 1 is an amino group, and then its position 3 is an amino group. The same numbering, the same bicyclic structure, but just slight difference in the substitution. Those are the 2 purines we have. And then you have the pyrimidines. And with the pyrimidines, of course, you have cytosine, uracil, and thymine. So when you look at cytosine again, numbering 1, this is position number 6. So position 1, 2, 3, 4, 5, 6. So that position 6 of cytosine, it has an amino group. Position again, and position 3 of cytosine, it has an oxo group. When you look at thymine will have some structural resemblance to uracil. So thymine and uracil have similar structures, with the exception of position number 5, where in thymine you have a methyl group, and in uracil you have a hydrogen. So that is thymine, 2 oxo groups at position 6, 1 and 2, and that is cytosine, an amino group at position number 6, and an oxo group at position number 3. The other thing to note is that in the DNA, you have cytosine and thymine. You do not have uracil. So in DNA, again, you have the pyrimidine, cytosine, and thymine. You do not have uracil. In RNA, that is where you have the uracil. So that's important again to note, because it makes a slight difference. And therefore, if you are having drugs that are affecting the synthesis of thymine, they might not affect the synthesis of the RNA. So now the structure, this is a single strand. So when you look at the DNA, it's a double strand. So after this base, there will be another, to arrange itself such that there's another base here. The same structure now, let's say you can draw a line here and get the mirror image. So kindly in your mind, put a line here as your mirror and get the mirror image, and this will come to the other side. So the base will be next to this, and then you will have a ribose, and you will have your sugar, your phosphate. So this is the backbone. So you can see the backbone on this side, and also on this side, because we have said the DNA has 2 strands together. So you find that there you will have this backbone of a ribose sugar and a phosphate. So when you bring in the other strand, on the end, you will also have the backbone of a ribose sugar and a phosphate. In the middle, you will have your bases. So you will have this base from this particular strand. I have asked you to draw a mirror here, and it would be good for you to draw out the whole thing. So you have if you put a mirror here, so you're saying the next base will be lying next to this. So there will be a base here, and then the ribose sugar, and then the phosphate. So this sugar will be lying next to another. So this base, will be lying next to a base, and the 2 bases will be joined with hydrogen bonds. So they are not bonded covalently. They are bonded through hydrogen bonds. And of course, you do know the bases that are bonded together. There is a way. There is those bases, a certain base binding another base. So we are only saying that in the middle of our DNA, which is a double helix, will be the bases, and at the ends, you will have the backbone of the ribose sugar and the phosphate. Backbone, ribose sugar, and the phosphate. And in the middle is where you have your bases. And that structure is very, very important for the drugs, because it is the drugs are able to utilize that structure to be able to get to have an influence on the replication. Because for this DNA to replicate, remember, it must first uncoil and separate. For it to undergo replication, it must uncoil and then separate. And one of the templates is the one which acts. One of the strands is the one which acts as a template, not both. So there must be the uncoiling, the separation, and then one of the strands acting as a template. So if you have an influence on the binding in the middle, if you have an influence such that this base and that base cannot uncoil and so on, then you will have a drug having preventing a replication to occur. Because we are saying for replication, you have the two strands. They must, first of all, the way they are coiled, first and foremost, they must uncoil. Number two, they must separate, so that one of the strands is what will act as the template during the replication. So once you do not allow them to uncoil, to separate, as we have said, then you will have a problem in the DNA replication. You have a problem in the DNA replication, you have a problem in mitosis. Now, of course, this was just to remind ourselves, but we have looked at them. We have adenine, guanine, thymine, cytosine, uracil. We have done these things. Just remind me of how these bases, how they pair. Remind me of how the bases pair. How do the bases, when you are forming, I have to keep giving myself a small break. When you are forming the DNA, can you remind me of how the bases pair? How do the bases pair in formation of the DNA? Can you move quickly? That's a bit. You told me you've done this. Then I think also you have also done them in biochemistry in first year. Yes, it's correct. That base pairing is very, very important. I can call it CGs. You know one, the other one becomes much easier, because we have said uracil is not part of the DNA, so you'll have thymine. So you just know one comes in. So the cytosine will pair with guanine. So if you are going to disrupt that base pairing, you will disrupt. Because if you disrupt that base pairing, you will change the type of bonding, types of bonds that are used, and again, you will impair the replication. So cytosine pairs with guanine, whereas thymine pairs with adenine. And that is good, thank you.